Okay, starting in chapter 3, what we're going to do is bring together graphs of original function, the derivative function, and the second derivative function. And then in second semester, we're going to take that into another level by not just looking at the derivative, but going backwards and looking at the integral. So let's do a quick pre-calc review. So we want to take this graph and label the local, absolute, maximum, and minimum. Okay, if you recall from pre-calc, maximum means something that looks like a hill, and then minimum means something that looks like a valley. So this is a hill, hill, hill. So these are all maximums. The question is what's a absolute and what's a local. Another way to say local maximum is relative maximum, or local just means relative. So the difference between absolute and local or relative is local is just saying around this area, this is the largest one, or around this area, this is the smallest one. But absolute means this is the all-time smallest place or all-time largest place. So for example, this part here, this would be a local maximum. This would be a local maximum because it is the highest around its neighborhood. This one would be a absolute maximum because it is the highest value of every place, because the graph keeps going down. Now, according to the book, this is also a relative maximum, or sorry, local. Let me just keep the vocab consistent. So by definition, something that is local, something that is absolute is also a local something. Here we have a local min and another local min here. There is no absolute minimum because the graph keeps going down. All right, so the extrema definition is that if you have a number c in the domain D of a function f, then f of c is the minimum of f on interval I when, let me put it here, f of c is less than or equal to f of x. F of x means, kind of all the other y values in that area for all x in the interval I. And then same thing, f of c is the maximum of f on interval I. Oops, sorry. When f of c is greater than or equal to f of x for all x in I. So that's kind of just a definition. Let's look at these graphs. These are kind of interesting. So what I want you to notice is the endpoints. So endpoints means that they can be open or closed, right? We can always have an open or closed interval. So let's take a look at what we call maximum and minimum. So for example, in this graph here, you can see that it's in a closed interval between -1 to 2. And then we have this minimum here, which we can pretty much say is an absolute minimum because the graph is not going to increase anymore. So this is absolute minimum, or we can say it's a local minimum because by definition, something that is absolute is also local. This one here is the absolute maximum because there is no other number that is bigger. And then however, this is not local Oops. Let me erase this. This is not a local max. This is a little bit confusing because endpoints cannot be local. Endpoints cannot be local. And why is that? Because there's nothing to compare to except for itself. So you have to compare to neighboring values. The only neighbor is on the left of it. There's nothing on the right. So because it has nothing to compare to on the right, it cannot be a relative maximum. What is this one here? This one is, let's see, this one should be local max. I'm sorry, this one cannot be local max. So this one's nothing. It would be a local max if this side goes down, but this is an endpoint, and endpoint cannot be a local. And the only other qualification it could try out for is absolute, but it's not an absolute maximum. So this one is nothing. All right, now look at this one. So I'm showing you kind of the weird graphs. So this is on an open interval, -1 to 2. See how it has two open circles? That means it's an open interval. This one, this is a minimum, and we can pretty much say this is an absolute minimum or local minimum. Both of them are okay. This one is not a maximum. So maximum or minimum has to be an actual point. So by definition, open circle just means you're trying to get to a end, but it's never actually reaching that number. So there's really no absolute number because there's no absolute point. Therefore, it cannot be a maximum. And so same thing here, nothing there. All right, this one. This one, it's on a closed interval. However, there is a discontinuity here. All right, this one, we called this point a minimum before because there was a point, but now there's a discontinuity. By definition, discontinuity, a hole, or anything that's open, cannot be anything because there's no solid, there's no defined, there's nothing defined there. So then you cannot say that is any kind of point there. So that is not a minimum. This is a maximum, or we can say this is an absolute maximum because that is the highest value in this interval. This one here is kind of strange. This one would be a relative max. This one's very strange. It would be a relative max because by definition, it is the highest number around its neighborhood. See how the neighborhood is the neighboring values? The neighboring values here, it is the highest out of its neighboring value, so that is a relative maximum. I know that is very strange because it's disconnected, but we're going with definitions. All right, now let's go to a theorem. This is called the extreme value theorem, EVT. So this is our theorem number 2. Remember, theorem number 1 was IVT, intermediate values theorem. So our second theorem is extreme value theorem. Extreme value theorem says, okay, or let's kind of get to the extreme value theorem. If a function is continuous on a closed interval, remember I said at the beginning of I don't know, the year, I said whenever some theorem or someone tells you some kind of theory, you always want to ask, okay, is it for every single, what kind of instance is it valid for? Is it for continuous functions only, or is it okay? Is it applied to any kind of function, even if it's discontinuous? And then the second thing you always ask is, on what kind of interval? Is it only on closed interval, or is it also for open interval? So make sure you kind of keep those two things in mind. This theorem is for continuous function on a closed interval. Okay, so on a continuous function in a closed interval, is it guaranteed that it has a maximum and a minimum? Okay, well, let's try. So whenever someone asks you a question, you always try to find all the ways it cannot happen. So let's before I do that, let's just kind of draw out what it's talking about. We want a continuous function, that means there's no break. And then it's on a closed interval, that means it has endpoints. So maybe something like this. Okay, if it's a continuous function with closed interval, is a guarantee that it will have a maximum and a minimum. I think it's, yeah, maximum and a minimum. Well, there is an absolute maximum here, and there's an absolute minimum here. So looks like it. Okay, well, let's try to draw something else. Maybe something like this. It's continuous on a closed interval. Does it have a maximum and minimum? It has a minimum here. Looks like we have two maximum here. If the way I draw it, they are the same level, then I have two maximums. So then let's kind of think about it. If a function is continuous, does it have a maximum minimum? Let's try the kind of the most extreme case. Straight line, straight flat line. Okay, it's continuous on a closed interval. Does it have a maximum minimum? Yes, the maximum is its minimum. So if you kind of think about it, just kind of think about extreme case. If you have something that's connected, if you have something that's connected, this is like the simplest case, right? Straight line. And the line has endpoints. If you have a line that it does not break and has endpoints, of course it has a lowest point and of course it has a maximum point. And so this is the extreme value theorem. If you have condition one, if the function is continuous and the function is on a closed interval, and then let's call this closed interval AB, the conclusion is f has both an absolute max and min. Okay, so this is the extreme value theorem. Okay, so let's look at another strange case. Explain where the absolute maximum and minimum occurs. If it doesn't occur, explain why. Well, on this one, we cannot use you cannot use the extreme value theorem because it's disconnected here. But let's just look at the graph anyways and kind of do what it wants us to do. Explain where the absolute maximum and minimum occurs. If it doesn't, explain why. All right, so if we look at this graph here, where is the absolute max? Absolute max means it has to be the absolute highest y value, right? So that would be here, except it is an open circle. So we cannot say that is an absolute maximum. That is probably, somewhere here is the absolute highest, but it's never a defined point. So then there is no absolute maximum. Okay, so no absolute maximum on this type. Okay, does it have an absolute minimum? Yeah, this one. This is the absolute smallest y value. What is this one then? Nothing. So remember, if it's an endpoint, the only thing it can qualify for is the absolute something. This is neither the absolute highest nor the absolute lowest, so this one qualifies for nothing. Then what about this one? This one is also nothing because around its neighborhood, it is not the highest or the lowest, so that is also nothing here. All right, now let's look at this one. This one, we also cannot use EVT because we have an open circle here. We have an asymptote here. The two ends are not closed. All right, so do we have an absolute max and absolute min? No. This one would be the lowest, except there is an open circle, therefore there's no defined point there. So this is nothing. Does it have an absolute maximum? Definitely not, This keeps going up forever because this is an asymptote, so you cannot say something that goes up to infinity is an absolute maximum. So this is also nothing. So absolute maximum minimum has to be an actual point. Now what we're going to do is take this graph and we're going to think about f of x. Sorry, f prime of x. So what that means is think about its derivative. Think about its derivative. So we had all these interesting points before, right? So we had the maximum here, minimum here, maximum here, minimum, maximum. All right, so that's so let's look at each one. What would be the derivative at this point? So derivative, remember, means the slope of the tangent line. So this tangent line would be a flat line there. So then what would be the derivative? That would be 0. What about this point here? What would be the derivative? That would also be 0. And then here, same thing. That would be 0. Same thing here. That would be 0. What about this one? That would be undefined. Remember, you cannot have derivative at a sharp point. And so what's interesting about maximum and minimum of the original graph being f of x, is that at the maximum and minimum of f of x, the derivative is 0. But not everything is 0, right? We had this one where it is a maximum of f of x, but the derivative is undefined because of the sharp corner. So let's say that for some reason someone says, please find the maximum and minimum of this graph of f of x, and you have very little things to work with, then what you would have to do is find the points that could qualify for maximum and minimum. And then what you would do is figure out whether the derivative is 0 or undefined. These points where we qualify them as possible maximum or minimum are called critical numbers. So this is a important vocab here. Critical numbers, or another way to say it, is critical point. These are points where f of x is equal to 0 or undefined. Because these are the places where it's possible to have a maximum or minimum. So let's write a few notes. So if f prime of c, so at this point, you have a derivative of 0 or undefined, then x equals c is a critical point. Or you can say critical number. Now, critical point may be maximum or minimum, but it's not guaranteed. Okay, so our task today is to just find a critical point, and then later on we're going to classify them as whether they're maximum or minimum, and so on. So find the critical numbers. Whenever someone says find the critical numbers, you're thinking, oh, okay, when the derivative is equal to 0 or undefined. So we need to find the derivative first. The derivative is equal to 12x cubed minus 12x squared. All right, equal to 0 or undefined. Well, this function is only possible to be 0. It's not possible to be undefined, so we're not going to check undefined. All right, so now just take out your algebra 2 skills, factor. So 12x squared times x minus 1. Remember, do not divide by 12x squared. If you divide by 12x squared, you're going to lose information because you got rid of x. So make sure you solve this way. All right, make each one equal to 0. So x is equal to 0 or 1. All right, that's it. This is kind of the easy part. We're just practicing finding critical numbers. All right, let's have you pause the video and give this a practice. Find the critical numbers of this function. Okay, the numbers are -1, 0, and 2. All right, let's try another one. This is a little bit trickier because now we're getting to harder derivatives. Find the critical numbers, so let's do this together. This one requires a product rule, or you can multiply them together and then you can just do power rule if you want. I'm not sure which one is easier. Maybe we'll do power rule. Okay, let's multiply this together. 4x to the 3/5 minus, when you multiply the ones with the same base, you add together the exponents, so that is 8/5. All right, so derivative of that, you get 4 times 3/5 times x to the 3/5 minus 1, so that's minus 2/5, minus 8/5 x to the 3/5. All right, we need to simplify this a lot. Okay, so let's see if you can kind of simplify this in your head as much as you can. So we're going to make this into a fraction. We know that this part is going to become a 12/5, and then this part is going to go into the denominator. So 12/5 with a denominator, so that changes to a positive. Minus, I'm going to just split them into numerator and denominator that way. Can see a little better. All right, I'm going to combine them into one big fraction because I am checking for what makes the derivative equal to 0, what makes the derivative undefined. So I need it to be a rational function. All right, so that just means I need a x to the 2/5 top and bottom here. So then I can add the two together. So 12 minus x, and then you have x to the 3/5 times x to the 2/5, that is just x, over 5x to the 2/5. All right, this is the derivative. So we are finding the critical numbers. That means make the what makes this function 0? Well, what makes this function 0? That's when the numerator is 0. What makes the function undefined? That's when the denominator is 0. So we're going to set the numerator 0 and then set the denominator 0. 12 minus 8x equals 0. Solve that. 12 is 8x, divide by 8. 12/8 is x, or that is 3 over divide by 4. That's 3/2. Denominator, 5x to the 2/5 equals to 0. This is pretty easy. It's just x equal to 0. I know that x cannot be 0 because it's making the denominator 0, but we're saying when x is what, then what number does x have to be so the function is undefined? Well, when x is 0, the function is undefined, which is what we want. So where are the critical numbers? This one and this one. Now, what we're going to do is take those critical numbers and we are going to try to find some absolute maximum or minimum on closed interval. All right, so to find the absolute extrema, so that is absolute maximum or minimum on a closed interval, it's very easy. What you're going to do is you're first going to make a table of endpoints since the endpoints are the only places that could really become absolute something. So we're going to check the endpoints and the critical points, right? Because critical points tells me that there is possibly a maximum or minimum there. So they are candidates for absolute maximum or minimum. So we want to put a table with endpoints and critical points. Next, we want to, from those points, find the f of x at each point. And when I say each point, I mean the endpoints and the critical points. Okay, and then very easy. The least is absolute min. The highest is absolute max. Okay, this is pretty easy, but make sure that you just do what I show you to do. All right, find the extrema on this interval. This interval is close, good. So the first thing we want to do is make a table with endpoints, right, where the closed intervals are, and then the critical points. So what we need to do is actually find the critical points. Critical points depends on the derivative. We already did this derivative before, but let's just do it again so we have it here. So this is equal to 0 because this is impossible to be undefined. So then let's solve. X is equal to 0 or 1. So those are my critical points, and then negative 1 and 2 are my endpoints. So what I'm going to do is make a table. X, f of x. I have my endpoints, negative 1, and then 0, 1 are my critical points, and then 2 is my other endpoint. What I'm going to do now is plug it into the original function. Please plug into the original function, because when we're saying the highest or the lowest, we are talking about the highest value or the lowest value of the original function. Please don't plug it into the derivative. If you plug it into derivative, you'll realize, how come I keep getting 0 on my critical numbers? So please be careful. All right, very easy, just plug it in. So 3 times negative 1 to the 4th minus 4 times negative 1 to the 3rd. That is 3 plus 4, so 7. All right, plug 0 in, 0. Plug 1 in, you get negative 1. Plug 2 in, 3 times 2 to the 4th minus 4 times 2 to the 3rd. So that is 3 times 16. 3 times 16 is 48. Minus 4 times 8. 4 times 8 is 32. So this is 16. So it's very easy. All you're going to do now is look for the highest number and lowest number. This is absolute max. This one is absolute min. Now, what we want to do is we want to be a little bit careful about what the question says, or kind of the wording of it. Okay, I know that we just kind of called everything absolute max, absolute min, but let's talk about the actual ways they can actually ask the question. So they may actually ask you for absolute maximum point. Point. If they actually say that, then you gotta give them the point. What's a point? Point is xy. So in this case, the absolute, what is it called? I said maximum. Absolute maximum point would be at 216. Okay. Another way they can ask is they would ask absolute maximum value. What does the word value mean? Value means y value. So what is the highest y value is what they're saying. Then you would say y equals 16. So please be careful or they can also say the x value of absolute maximum. If they say that, then you would say x equals 2. So make sure you read the question very closely on what they want, because you may find the right thing, but you answer the wrong question. All right, very easy. So let's kind of review. If they want the absolute something, you do 3 things. Number 1, make a table of endpoints and critical numbers or critical points. Number 2, find the f of x, not f prime, f of x at each point. And then third, the highest number is the absolute maximum, the lowest number is the absolute min. All right, let's have you try one. So find the extrema of 2 sine x minus cosine 2x. So a quick review of what is it called? Trig functions. I'm gonna guess that a lot of you kind of forgot your trig. So let's kind of do it together. Let's find the derivative first. F of x is equal to 2 cosine x minus plus sine 2x chain rule times 2 equals 0. All right, 2 cosine. Okay, let me rewrite this. 2 cosine x plus 2 sine 2x equals 0. I'm going to get rid of the 2's from everything. Not essential here. All right, we get to this point, we need to solve. Well, this is a little bit harder to solve. Hopefully you remember from pre-calc, this is not solvable. This is x, this is 2x. They have different variables, you cannot solve. So you got to get them either both into x or both into 2x. Easiest way is to get them both into x. And that means you got to change sine 2x, which means you got to remember double angle formula for sine. You do not need it for the AP test, but you might need it for homework. So there is a, what's it called, like a menu or table content of formulas at the beginning of the book, so you can check that out. Or you can always Google. 2 sine x cosine x is sine 2x. And now everything is in terms of x. What you can do is just solve this. I'm going to take out the cosine here. So 1 plus 2 sine x equals 0. So cosine x is equal to 0, or 1 plus 2 sine x is equal to 0. Okay, finding the critical numbers. What makes cosine 0? Within the interval 0 to 2 pi, that is 1 unit circle. So let's try to recall what makes cosine 0. That is at pi over 2 and 3 pi over 2. If you can't remember, of course, take out your unit circle and look at it right now, but just, know that you gotta memorize it. All right, let's solve this. So this is sine x is equal to negative 1 over 2. Again, think about your unit circle. What makes sine? Sine is the y value equal to negative 1/2. All right, that is 7 pi over 6 or 11 pi over 6. All right, now what we're going to do is take out our endpoints, 0 and 2 pi, and then put in our critical values, which are, I'm going to go from the smallest to highest. So pi over 2, 7 pi over 6, 3 pi over 2, oops. 11 pi over 6, and then 2 pi. And I'm going to evaluate it in this function. So let's go ahead and have you evaluate it and then come back and check. So that way you can kind of review and practice the trig functions. All right, please take a look at the values. You can see here that this one is the highest number, so this is the absolute maximum. There are, in fact, 2 numbers that are the same lowest number, so they're both absolute minimum. Let's just take a look at the question again, just to make sure we are answering the right question. Find the extrema, so it doesn't say value or point. So I think the table is good enough. Okay, and that is it for this lesson.